Okay, this is exercise 2.12. It says determine which of the following sets are spanning sets. Now it looks like the vectors that I've given here are the same as the vectors from exercise, I don't know, 2.7. I forget what we just did. Where it was asking you to determine which sets were linearly independent. Okay, I'm going to start with number 3. So we'll look at the third set of vectors: 1, 0, 1. 0, 1, 0. Now remember what it means to be a spanning set. It means that we can always find a solution to this equation no matter what x, y, and z are. So no matter what x, y, and z are, we can always find a solution to this equation. Now what this means in terms of matrices and row reduction: when we put this system into an augmented matrix and we row reduce it, we're never going to have a row of zeros. If it's a spanning set, there's not going to be a row of zeros here followed by a 1 on the right-hand side. So never a row of zeros followed by a non-zero. So we're never going to have a row that looks like 0, 0, 1 or 0, 0, 2 or 0, 0, 7.5 or whatever. Okay, now equivalently, that's equivalent to saying that if you row reduce just this matrix and you put it into, say, row echelon form, you'll get some matrix, no row of zeros. Okay, because if there is a row of zeros, then what it means is you can find some values for x, y, and z such that when you augment this matrix with the x and the y and the z, you're going to end up with a 0, 0, and a 1. Okay, which means that whatever vector you started with is not in the linear span of these two vectors. So this is the procedure. If you have a set of vectors, v1 through vk, and you want to know whether or not they're linearly independent, whether or not they form a spanning set, you put them into a matrix, row reduce, get it into row echelon form, and they are a spanning set if and only if there is no row of zeros when it's in the row echelon form. And actually, if there is a row of zeros at any step going from the beginning matrix to the row echelon form, if there's ever a row of zeros, then they're not going to be a spanning set. So they are a spanning set if and only if there is no row of zeros in the row echelon form. Okay, so for this specific example, we have 1, 0, 1, 0, 1, 0. Okay, and so the first thing that we need to do is swap the second and third rows. So this is 1, 0, 1, 0, 0, 1. Now I'm going to subtract the first row from the second row. So this is 1, 0, 1 minus 1 is 0, 0 minus 0, 0, and then I'll leave the third row alone. Okay, and now, so notice it's not in row echelon form, but there's a row of zeros. So we could stop right there and say there's a row of zeros. So it's not a spanning set. Okay, let me just go one step further. 1, 0, 0, 1, 0, 0. Okay, so what we have seen here is that there is a row of zeros. It's in row echelon form. There's a row of zeros, so it's not a spanning set. So in other words, there's some vector that is not in the linear span of the given two vectors. Okay, because what we're going to have, in other words, what my claim is, there is a vector. I don't know what it is, but I'm telling you, my claim is that there's a vector x, y, z such that when you put it into row echelon form, you're going to get something like this. And there's going to be a 1 here, and those can be whatever you want them to be. It doesn't matter. They could both be zeros. They could both be ones. They could both be whatever. But the bottom equation says 0 is equal to 1. Okay, so that is the procedure. You take the vectors, put them into a matrix, get them into row echelon form. If there's ever a row of zeros along the way, then they are not a spanning set. Okay, so let's I want to go over that. I want to just to validate this claim here. Okay, so what I want to do is I want to construct a vector xyz that satisfies this property. That when you put it into row echelon form, the right-hand side is going to be 0, 0, 1. And the way that I'm going to do that is I'm going to start with what I end up with. So 1, 0, 0, 0, 1, 0, 0, 0, 1. And I'm going to undo the row operations to get back to this matrix. Okay, so the last row operation I did was to swap the second and third rows, so I'm going to swap them back. So this is 1, 0, 0, 0, 0, 1, 0, 1, 0. That's what that row operation was. That row operation was subtracting row 1 from row 2. So I'm going to add row 1 to row 2. I'm going to add row 1 to row 2. So this is 1, 0, 0. This is 1, 0, 1. And this is 0, 1, 0. Okay, and then that row operation there was to just swap the second and third rows. So I'm going to swap them back. 1, 0, 0, 0, 1, 0, 1, 0, 1. Okay, and notice that these two vectors, 1, 0, 1 and 0, 1, 0, these are the vectors we started off with. So in other words, this is the right-hand side. So what this tells us, we explicitly constructed a vector, 0, 0, 1, that is not in the linear span of the given two vectors. Okay, and how do you know that? Well, what I just did was to construct a vector, but now to show this does what I say it does, just row reduce this matrix, 1, 0, 1, 0, 1, 0, 0, 0, 1, and you're going to get back to this matrix here, which has a 0, 0, 1 row, which means there's no solutions. Okay, so that's just sort of why we can put the vectors into a matrix and row reduce. And if we have a row of zeros, that means they are not a spanning set. And if there is no row of zeros, it means they are a spanning set.